Okay, good morning. So we are in the middle of defining the semantics of Haskell. And we've started to define domains for different types. So for the base types, we had these flat domains where you have one element for undefined and everything else is completely defined. So something like z bottom or the booleans with bottom and so on. We had product domains. So if you have several domains, you can build a cross product between them and you get a new domain. And we had functions. So functions from a domain D1 to D2, but not all the functions. We will not consider all of the functions, but only certain functions, because not all functions are computable, and moreover, we would like them to have certain nice properties. So the functions that we look at are monotonic. So we restrict ourselves to monotonic functions. And we will see another restriction today. So even the monotonic functions are too many, so we will do another restriction today. Namely, we will restrict ourselves to continuous functions. But we will see this later. And, well, to define the semantics of objects of base types, that is rather straightforward. So if we have a Haskell expression 5, the semantics will be the number 5. If we have a Haskell expression which is a tuple of, say, 5 and 8, then the semantics will be the tuple of the two numbers 5 and 8. The most interesting question is, how do we define the semantics for functions, in particular for functions which are defined recursively? So these are the domains. And then how do we define the semantics? The most interesting or most problematic case is to define the semantics of functions that are defined by recursion. So semantics of recursively defined functions. And we will do this by defining the semantics as the limit or as the least upper bound of a certain chain. So this will be defined as the least upper bound, lab for short, of a chain of functions. So what is a chain? Now the projector is working, so now we can read what is on this slide. Do I have to close this window? Maybe yes, then it's easier to read this, and it will also get colder. Okay, now it should be readable. So monotonic means a function is, if you have a function from D1 to D2, it's monotonic if you have the following property: if D is smaller than D prime, then you also have that f of D is smaller or equal than f of D prime. So that's monotonic. And a chain is simply a set, and the elements of the set can be ordered in such a way that one element is less or equal than the next element, this is less or equal than the next element, and so on. So a chain basically is a ascending sequence of elements, but we consider it just as a set. Now, as I said, we will define the semantics of recursively defined functions as the limit or as the least upper bound of some suitable chain. So, for example, if we want to define the semantics of the factorial function. Now, imagine factorial function, you programmed the factorial function in Haskell, you want to define what the semantics is. Then we will define the semantics as follows. We will build this chain of functions fact0, fact1, fact2, and so on. And this is indeed a chain. And why is it a chain? Well, these functions become more and more defined. Fact 0 is completely undefined. Fact 1 is defined for x which are smaller than 0 and for 0. So for all x until 0 it is defined, afterwards it's undefined. Fact 2 is defined until 1 and afterwards it's undefined, and so on. And on those arguments where they are both defined, fact 1 and fact 2 coincide, and so on. So these functions become more and more defined, and the limit that you reach, so the least upper bound of this chain, is this function fact, which happens to be the factorial function. So this really computes the factorial for all positive numbers. It's only undefined for bottom. So this is how we are going to define the semantics of recursively defined functions. And now, of course, the question is, can we be sure that such a least upper bound always exists? And in order to be sure that it always exists, we have to restrict ourselves to complete partial orderings. So what does it mean to be complete? So on domains, this less defined or equal relation should be complete. So it should be, so in other words, it should be a complete partial ordering, and then we can be sure that every chain indeed has a least upper bound. So what does it mean to be complete? Complete simply means an ordering is complete if two conditions hold. One condition is there must be a smallest element, which we denote by bottom, and indeed every chain has a least upper bound. So whenever you have a set and you can order the elements of this set, then there is an upper bound, and there is not only an upper bound but also a least upper bound, and this least upper bound is contained in D. So if you look at these factorial functions, fact 0, fact 1, fact 2, and so on, this chain has a least upper bound, namely fact, and fact has to be contained in the set D as well. And now, indeed, for all those domains that we looked at up to now, so for these three sets, this less defined or equal relation is complete. And this is the theorem that we have to prove now. So the domains that we looked at up to now are complete. So this is theorem 2.1.13 about the completeness of the domains that we had up to now. So we have domains D1 to Dn. Now, how did our domains look like up to now? Well, in the first case, we have these flat domains. Now, if we have a flat domain, then this less defined or equal relation is complete. And in fact, this doesn't only hold for flat domains, but it holds whenever all chains are finite. So if chains are only finite, then there always exists a least upper bound. So every reflexive partial ordering or partial order that has a smallest element, we need this in order to be complete, that has the smallest element and where all chains are finite, every such partial order is complete. And therefore, so thus, on all these flat domains, Z bottom, B bottom, and so on, they are all complete partial orders. So we can be sure for those base types, every chain has a least upper bound, and this least upper bound is contained in the domain. Now, how does it look like for product types? Well, for product types, everything works well again. So if this less defined or equal relation is complete on D1 and complete on D2 and complete on Dn, then less defined or equal is also complete on the cross product of D1 to Dn. So if this less defined or equal relation is complete for all I, then D1 cross Dn is also a complete partial order. And for functions, it works well again. And here, in fact, we only need it, so if we have functions from D1 to D2, we only need that less defined or equal has to be complete on D2. That's already enough to ensure that less defined or equal is complete on the functions. So if this is a CPO, a complete partial ordering, then less defined or equal on the functions is also a complete partial order. So in other words, if we start from our base types, Z bottom, B bottom, and so on, and then we build tuples or we build functions, we can be sure always this less defined or equal relation indeed is complete. So whenever we build a chain, the least upper bound will exist. Now this is not so difficult to prove. So I will prove A and B, and the proof of C is very similar to the proof of B, so I will omit this. So this is the proof of A and B, and C is similar to B. Okay, A says if a chain is finite, then it also has a least upper bound. That's what it basically says. So let's look at a chain which is finite. So a chain is simply a set of elements, D1 to Dn. Now it's a finite chain, therefore it has just n elements. And if it's a chain, you can order them. So let's say we can order them like this. D1 is less than or equal to D2, which is less than or equal to D3, and then finally we have less than or equal to Dn. Now, the claim is every finite chain has a least upper bound. Do you know how the least upper bound of this chain, what the least upper bound of this chain is? So least upper bound means it's bigger or equal than every element in here. And least upper bound means it's the smallest such upper bound. Now there are not many possibilities. What is the biggest element in this set? Well, it's Dn, right? Dn is bigger than Dn minus 1, bigger than Dn minus 3, bigger than D1. So Dn is obviously an upper bound, and it's clearly the least upper bound. So the least upper bound. So the least upper bound indeed exists. It's Dn. And why is it? Well, in order to prove that something is the least upper bound, we need two properties. It's an upper bound. So it's an upper bound since all these di's are less or equal than dn by transitivity. And why is it the least upper bound? Well, let's assume there's another upper bound. So if E is also an upper bound of S, in order to show that Dn is the least upper bound, it has to be smaller than every other upper bound. Now, if E is another upper bound, we have to show that Dn is smaller than E. Okay, but if E is an upper bound of S, that means E is bigger than every element of S. Every element of S. Dn is also an element of S, so E has to be bigger than Dn, otherwise it wouldn't be an upper bound. Then Dn is less or equal than E, since Dn is an element of S. So if you have a finite chain, well, then one of these elements in there is the biggest element, and that's the least upper bound. Now, how does this work for product types? Now we look at the domain D1 cross D2 cross Dn, and we have to prove that these two properties are fulfilled. Now the smallest element of D1 cross Dn. Now this really has a smallest element, and we know how it looks like. It's the tuple where the first component is the smallest element of D1, the second is the smallest element of D2, and the last one is the smallest element of Dn. So property 1 is fulfilled. So this is property 1. And for property 2, we have to show that every chain has a least upper bound. Okay, so let's take a chain. So this is a subset of D1 cross D2 cross Dn, and let this be a chain. So this is a subset of this set. In other words, it looks like this. So it has elements which are tuples. So let's say the first one looks like this, D1 to Dn, and I write an index 1 on top. The next one is D1 to Dn with index 2, and so on. Now this can be finite or infinite. If it's finite, then it clearly has a least upper bound. Every finite chain has a least upper bound. So the only interesting case is if it's not finite. And let's say we can order these elements such that D11, this first tuple, is less than or equal to the second tuple and so on. Now, we know how the comparison of tuples works. The comparison of tuples works component-wise. So this tuple is less or equal than this tuple if the first component here is less or equal than the first component there, second component here is less or equal than the second component there, and so on. So we have the following thing. We have D1I is less defined or equal in the domain Di than D2I, and so on for all I. So if we take, for one of these i's, so one of these i's between 1 and n, if we take the ith components, then we get a chain again. So Si, and these are the projections on the ith component. So this is D1i, D2i, D3i. This is a chain for all I. Now what we want is the following. We want to prove that S, this chain on tuples, has a least upper bound. And the reasons we want to prove that on this tuple domain, the less defined or equal relation is complete. What we know is that on D1 and on D2 and on D3 and on Dn, that on all these component domains, there, less defined or equal is already complete. So if we have a chain of elements from D1, then there exists the least upper bound. If we have a chain of elements from Dn, again, there exists the least upper bound. Now, this is a chain of elements from Di. So this Si is a subset of Di. So this is a chain of elements from Di, and we know that less defined or equal is complete here. That's the prerequisite of the theorem. So since this is complete, there exists the least upper bound of Si for all I. So if we just look at the projections, then we get chains again, and these chains have least upper bounds by the prerequisite. Okay, and now we are done, because then if all these projection sets have least upper bounds, then the original set has a least upper bound as well, and the least upper bound is simply the tuple where the first component is least upper bound of S1, the second is least upper bound of S2, and so on. This was a lemma that we proved in the last lecture. So this was the lemma 2.1.11a. Then the least upper bound of S exists as well, and we even know how it looks like. It is the tuple where the first component is the least upper bound of S1, and the last one is the least upper bound of Sn. So what this theorem says is, if you have a domain where less than defined or equal is a CPO, and then you can combine these domains by building cross products or by building function domains, and again, this ordering remains complete. So we don't have to worry about the question, is there a least upper bound? We can be sure every chain has a least upper bound. Okay, so this is nice to know, but the domains that we really use are not quite the ones that are up there, but for functions we do some restrictions. We have already done a restriction by saying we don't look at all functions, only monotonic functions are interesting, and now we will do another restriction, and we will restrict ourselves to continuous functions. So instead of using something like D1, all functions from D1 to D2 as the domain for functions, we restrict ourselves to functions that are monotonic. We had that already. And moreover, they should also be continuous. And indeed, we will continuous, in German stetig. And indeed, this is used to rule out some non-computable functions again. So all computable functions are monotonic and continuous. Monotonic and continuous. Okay, so what does continuous mean? I'll write down the definition first, and then I will explain it with a nice diagram and with several examples. So, what are continuous functions? Now, I mean, this notion of continuous functions, stetige Funktion, you know from mathematics, and here it means the same thing. So it's no big surprise. It's like monotonic. The notion monotonic is also not new. The only difference is we only regarded monotonicity with respect to this less defined or equal relation. And here we have the same thing. Here, this is the notion continuous from mathematics, but in the special case where we regard this less defined or equal relation. Okay, so how is it defined? Now, we take functions from D1 to D2, and we now assume that both D1 and D2, the relation less defined or equal, is a CPO, so it should be complete. Every chain should have a least upper bound. So let this be D1 and D2. The relation should be complete. Now, a function from D1 to D2, so f goes from D1 to D2, is continuous if we have the following thing. Whenever there is a chain of elements of D1, then it doesn't matter whether you first compute the limes, or the least upper bound of this chain, and then apply f, or whether you do it the other way around. First apply f, and then compute the limes. So in other words, computing least upper bounds and applying f can be exchanged. That's what continuous means. So for all chains S of D1, we must have the following thing. If you first take S, compute the least upper bound, and then apply f to this least upper bound. Now this means take the chain, compute the least upper bound, and then apply f to this element, which is the least upper bound of this chain. This should be the same as first applying f. So you take all the elements from the chain, and you apply f to every element, and then afterwards you compute the least upper bound. So here this means first compute least upper bound, then apply f, and here's the other way around. First apply f, then compute the least upper bound. Now I will illustrate this with a diagram and some more examples. And the set of all continuous functions from D1 to D2, from D1 to D2 is denoted. Now we denote this as follows, not D1 arrow D2, but we do some angle brackets around it. Now this notation is non-standard in the literature. This is normally not denoted with these angle brackets, but with square brackets. But this leads to a confusion with Haskell notation. This looks like a type, a list type. I mean, in Haskell you write lists with square brackets, so this would be confused with the type where you regard lists and the elements of these lists are functions. So in order to avoid this confusion, I use different kinds of brackets here. So in the literature you normally find this, but this might lead to confusion with list notation in Haskell. So if you look into a book on functional programming or on semantics, you will find this notation and not this notation. Okay, but I hope this is not very confusing. It's just notation. Now, we also sometimes write instead of writing this, so this is a set where we take all elements D, so S is a subset. We take all elements D of S and apply F to them. And instead of writing something like this, we also simply write not F applied to an element, but F applied to a whole set. So if we write F and then not a single element, but the whole set, this is a short notation for this. So this means this is the set where F is applied to every element of S. And then continuity can be reformulated even simpler. It should be the same whether you first take S, then apply least upper bound, and then apply F, or whether you do it the other way around. You first take S, then apply F, and then build the least upper bound. So you can exchange F and least upper bound. This is what continuous means. Okay, I will explain this after I wipe the board. Okay, so let me try to illustrate this with a diagram. Now, so continuous means if you have a chain. Now let's write down a chain. So a chain is simply a set of elements, D1, D2, D3, and so on, which are increasing. So D1 is less than or equal than D2, D2 is less than or equal than D3, and so on. So they get bigger and bigger. And now a chain, we work in with complete partial orders, so this chain has a least upper bound. So they get bigger and bigger, but you can build a limes here. So a least upper bound, and then you get D. So this here is the least upper bound of S, where S is D1, D2, and so on. This is D. Now, if F is continuous, then it doesn't matter whether you first build this least upper bound and then you apply F. Now, if you here apply F, you get F of D. Or in other words, this is F of the least upper bound of S. Now, this is the one direction. You can first build the least upper bound and then apply F. Now, of course, you can also do it the other way around. You first apply F. So you apply F on every element. So if you apply F here, you get F of D1. If you apply F here, you get F of D2. If you apply F here, you get F of D3, and so on. And if F is monotonic, let's assume this for the moment, then you even have this. And now, if F is continuous, then if you build the least upper bound of this chain, you arrive here again. Now, if this holds, this is a chain, so it has a least upper bound, but the least upper bound of this chain is not necessarily the same as this. If F is continuous, then it is the same. So then you can build here the least upper bound and arrive here again. So this only holds if F is continuous. So if F is continuous, then it doesn't matter whether you first apply the least upper bound and then apply F, or whether you go in the other direction, you first apply F and then build the least upper bound. Now let's look at some examples. Now the first example are constant functions. Constant functions are always continuous. Now, why is this the case? Now let's look at a constant function. So f is a constant function from d1 to d2, and constant means no matter what argument you apply to, you always get the same result. So f of x is the same element e for all x from d1. Now, why is this continuous? Let's try to prove it. Continuous means we take an arbitrary chain of elements from D1, and then it should not matter whether you first build the least upper bound of this chain and then apply f, or you first apply f and then you take the least upper bound. So let S be a chain. Now, what is f of the least upper bound of this chain? Now, the least upper bound of S is some element of D1. We don't know how it looks like, but luckily we know what f does, because f is a constant function. F always returns e for every argument, so also for this argument. So this will be e. And what is the least upper bound of f of S? Now, this is the least upper bound of f of d, where d comes from S. So we take all the elements from this chain and apply f to every element. So what is f of d if we take some element of S? It's e. So this set only contains e. So we have to take the least upper bound of this singleton set, which only contains e. Okay, so the least upper bound of this is e, and indeed it's the same. So it doesn't matter whether you first build the least upper bound and then apply f, or you do it the other way around. Constant functions are continuous. Okay, constant functions are not very interesting, but at least we have one example for a continuous function. Now let's look at another example. So the next example is the identity function. So identity function is the following. It's a function from d to d, so now d1 and d2 are the same. And the identity function should return I of x should be x for all x from d. Now again, the claim is this is continuous. Let's prove it. Okay, so let S be a chain. So what happens if we first build the least upper bound and then apply the identity function? So what will be the result here? Well, the identity function returns its argument, so it will be the least upper bound of S. Nothing changes. Now let's see what happens if we do it the other way around. So now we first apply I, the identity function, to every element in S, and then we take the least upper bound. So if I write it down in usual notation, this would be I of d for every element of S. Now I of d is the same as d, right? I is the identity function. So this is d. So this is the set of all elements d from S. Now this we can also write down in a short way by simply writing S. These are all elements of S. So in other words, this is the least upper bound of S, and indeed we get the same thing. So it doesn't matter whether you first take the least upper bound and then apply the identity function, or you do it the other way around. Now that's no big surprise, because the identity function doesn't do much. I mean, there's nothing to be precise. Now, let's look at a more complicated function. I mean, up to now we have only seen functions that are continuous, so now the question is, how would a function look like that is not continuous? Here is a function which is not continuous. So this is an example for a function that is not continuous. Now, I have already mentioned all computable functions are continuous. So if we want a function that is not continuous, the function will be not computable. Therefore, it will look a little bit more difficult than identity or constant functions. That's unavoidable if you want to have something which is not computable. So we take a higher order function, g. And what g does is it takes a function as input. It takes a function from z bottom to z bottom. So some function which maps integers to integers and returns an integer or bottom. And it should be defined like this. So g takes some function f as input, and it either returns 0 or bottom. So this is the bottom element of that bottom. Now, what it does is it checks whether this function f is total. If f is total, it returns 0. If f is not total, it returns bottom. So total means f never returns bottom unless you apply to bottom itself. So f of x is always defined. It's never bottom for all x, for all integers. So for bottom, f might return bottom, but if you apply f to 0 or 1 or 2 or 3, it should be defined. So in other words, if it returns 0 if f is total, if it's defined everywhere. And otherwise, we return bottom. So this function is not computable. Now we had the halting problem is not decidable, so you cannot find out whether evaluation of some expression will terminate or not. But this problem is even harder. This problem is the totality problem. Here you take a function f and you want to find out not is it defined on some certain argument, you want to find out is it defined on all arguments. Will it always terminate no matter what argument you apply it to? Now this question is not even semi-decidable, and G is a semi-decision procedure. G, if f is total, then G finds this out and gives us 0. If f is not total, okay, then G might fail and be undefined as well. So, well, in common, normally something like G is called a termination analyzer. And now something like this cannot exist. It cannot always find out whether functions are total. So G would be a semi-decision procedure for the totality problem, and the totality problem is not semi-decidable. But since the totality problem is not semi-decidable, semi-decidable means if it holds, then your semi-decision procedure terminates and finds this out. If it doesn't hold, then your semi-decision procedure might be undefined. But since the totality problem is not semi-decidable, G is not computable. So we would like to exclude functions like G, and indeed we will manage to do this because G is not continuous. However, G is monotonic. So if we only exclude non-monotonic functions, G would not be excluded because it's monotonic, but it's not continuous. So let's see why this is not continuous, but why it is still monotonic. So this is an example for a function that is not continuous, but monotonic. Okay, let's first show that it's monotonic. Now, monotonic means if f1 is less defined or equal than f2, then we also have that g of f1 is less defined or equal than g of f2. Now, why is this the case? Now, well, let's take two functions, f1 and f2, and let's say f1 is less defined or equal than f2. Now, the first case is f1 is equal to f2. Okay, if f1 and f2 are equal, then g of f1 and g of f2 will also be equal. So, in this case, we clearly have this claim. So the interesting case is they are not equal. Now, if they are not equal, but f1 is less defined than f2, then this means there is some argument, x, where f1 of x is less defined than f2 of x. Because this is defined argument-wise. A function is less defined than another function if for all arguments f1 of x is less defined or equal than f2 of x. And if they are not equal, well, then they can't be the same on all arguments. They must be different somewhere. And at that point where they are different, f1 of x must strictly be less defined than f2 of x. So there is some x where f1 of x is less defined than f2 of x, and they are not equal. For some x. Now this here is the less defined or equal relation on z bottom. Now if they are not equal, and this thing is less defined than that, z bottom is a flat domain, then there is just one single possibility. Then f1 of x must be bottom. Otherwise they would be equal. So since z bottom is flat, we know that f1 of x is bottom. Okay, so now there are two possibilities. X is bottom or x is not bottom. If x is not bottom, then this means f1 is not total. There is some x which is not bottom where f1 is undefined. Then f1 is not total. And therefore, and thus, g of f1, if it's not total, then g of f returns as bottom. So this will be bottom. And bottom is smaller, less defined or equal than anything. So it will also be less defined or equal than g of f2. And in the other case, okay, so if f1 and f2 differ on some x, which is not bottom, then we are done. And otherwise, if f1 of x is the same as f2 of x, for all integers, but they only differ on bottom, which could be but then g again gives us the same. So g only looks at what f1 and f2 do outside of bottom. Now they're the same. If they're both total it will return 0 for both of them. If they are both not total, it will return bottom, but it will be the same. So then we would have g of f1 equals g of f2. So if f1 is less than or equal than f2, then it depends on where they differ. If they differ on an integer, then g of f1 will be bottom, and therefore smaller than g of f2. If they differ somewhere else, then g of f1 and g in f2 will be the same. And if they don't differ at all, then g of f1 and g of f2 will also be the same. So it's monotonic. But g is not continuous. So in other words, there is a chain, and for this chain it matters whether you first take the least upper bound and then apply g, or you do it the other way around. So we have to give basically a counterexample to continuity. So we have to find a suitable chain. And, well, we need a chain of functions. We need a chain, g is a function which takes functions and maps them to integers. So we need a chain on the set z bottom, arrow z bottom. So, for example, we can take this chain, fact 0, fact 1, fact 2, fact 3. So let's take this chain, fact 0, fact 1, and so on. Now, what happens if we first apply the least upper bound and then apply g? And what happens if we first apply g and then take the least upper bound? Now, the least upper bound of S. The least upper bound of this chain here is this function fact. So this is g of fact. Fact is this function. What g does is it checks whether its argument is defined everywhere except for bottom. Now this function is defined everywhere except for bottom. So this is a total function. The factorial function is total. So g will return 0. Since fact is a total function. And now here, we take the least upper bound of this set. It's the set where g is applied to all the elements of S. Now the elements of S are fact 0, fact 1, and so on. Now how do they look like? For fact 0, g checks whether it's a total function. Now fact 0 is clearly not a total function. It always returns undefined. Now, so since fact 0 is not total, g returns bottom. Now fact 1 is also not a total function. It's defined more often, but for x's which are greater or equal than 1, it's not defined. So fact 1 is also not total. Fact 2 is also not defined everywhere. If you make x greater or equal than 2, then it's not defined. So all these fact 0, fact 1, fact 2, and so on, they are not total. They get more and more defined, but if you take an argument which is big enough, then fact is not defined. So here you always have bottom. The reason is fact n of x is bottom if x is greater or equal than n. So all these functions in this chain are not total, so here you have bottom. Okay, and the least upper bound of this set, which only contains bottom, is bottom. And bottom is not the same as 0. So g is not continuous. So to make it more intuitive, what does continuous mean? So intuitively, a function is continuous if its behavior on the limes So here you have this set of functions, and the limes of these functions is fact. And if the behavior on the limes of a chain can be computed by simply applying the functions to all the elements of the chain. If it's behavior on the limes or on the least upper bound of a chain can be determined by its behavior on the elements of the chain. And here this is not true, because if we want to find out how G behaves on the limes of this chain, we can look at all these elements of the chain and find out how G behaves on these elements in here, but this doesn't help us. Because on these elements in here, G behaves like this. It gives us bottom. But from this, we cannot find out that on the limes of this chain, it would give us 0. So this function cannot be computed by only looking at finite approximations. It can only be computed by being more intelligent and really finding out how the least upper bound looks like. And that's the reason why it's not computable. A computable function has to be determined by finite approximations, and this doesn't work with G here. So functions like G we don't like, because functions like G are not computable. We don't need them in our semantics, and we will exclude them. And you can see that indeed there are monotonic functions, G is monotonic, that are not continuous. G is not continuous. So there's some continuity is something which seems to be harder than monotonicity. And well, we know that monotonicity clearly does not imply continuous. Now this example here showed this. This is monotonic but not continuous. So the question is, does the converse hold? Is every function that is continuous also monotonic? And we will answer this question in the next theorem. So the following theorem clarifies the relationship between continuous and monotonic. This is theorem 2.1.15, and it gives us the connection between monotonicity and continuity. Okay, so we need two sets, D1 and D2, and the less defined or equal relation should be complete. So these should be CPOs, complete partial orders. And we need a function from D1 to D2, a function f. And part 1 is f is continuous if and only if f is monotonic and so by seeing this beginning of this theorem, you can already see that this arrow indeed holds. So if f is continuous, then f is also monotonic. So monotonicity does not imply continuity, but continuity does imply monotonicity and something else. So continuity is a bit more than monotonicity. It's monotonicity plus something. And the something is 1/2 of the continuity condition. So for continuous functions, you have this. This must be the same as this. It shouldn't matter whether you first build the least upper bound and then apply f, or whether you do it the other way around. This has to be equal. That's the definition of continuity. If you know that f is monotonic, you don't need equality here, but it's enough if this thing is less defined or equal than that. So that's the... So now we can see that continuity is a bit more than monotonicity. It's monotonicity plus this direction. The other direction follows from monotonicity. Okay, we will see why this is the case. But in the easy cases where chains are finite, there's no difference between monotonicity and continuity. So in order to find something which is monotonic and not continuous, we needed an example which was a bit more complicated. Because if you just look at domains where the chains are finite, monotonicity and continuity is the same. So if D1 only has finite chains, then indeed F is continuous. Continuous. It's a difficult word. Continuous if F is monotonic. So this difference only plays a role if there are chains of infinite length. Okay, we will prove this theorem and start with A. Okay, let's first prove the direction from left to right. So let's assume that F is continuous. So let F be continuous. Now then we have to show two things. We have to show that then F is also monotonic, and moreover that this relation holds. Now this relation is trivial because continuity means that these two things are equal. If they are equal, then then this is also less defined or equal than that. So this means these two things are equal. And hence, we also have that this is less defined or equal than this, since this less defined or equal relation is reflexive. So this is trivial. The interesting case is, why is F monotonic? Why does continuity imply monotonicity? So we show that F is monotonic. So what does monotonic mean? Monotonic means if I take two elements, D and D prime, and D is less defined or equal than D prime, then also F of D must be less defined or equal than F of D prime. So let's take D and D prime, and let's say D is less defined or equal than D prime in D1. And what we have to show is that then F of D is less defined or equal than F of D prime. Now, why is this the case? We know that F is continuous. And we know that D is less than or equal to D prime. Then why should this hold? Now, continuity says something about chains. How can we make a chain? We have two elements, D and D prime, so we can make a chain out of them. So let's say D, D prime, we take this set, and that's clearly a chain, because you can order these elements. D is less than D prime. So this is a chain. What's the least upper bound of this chain? So we need an element which is greater or equal than both D and D prime, and which is the smallest such element. Now, there are not many choices. D is not a good idea, but D prime is a good idea. D prime is greater than D, and it's greater than or equal than D prime. So the least upper bound is D prime. Okay, now since F is continuous, we know that it doesn't matter whether you first apply least upper bound or you first apply f. Now what is this? The least upper bound of S is is d prime. So this thing here is f of d prime. So f of d prime is the least upper bound of this. Now what is this? This is the least upper bound of f applied to all the elements of S. So there are just two elements, f of d and f of d prime. So what this says is that f of d prime is an upper bound of f of d and of f of d prime. Now if this is an upper bound, f of d prime is an upper bound of fd, then this means f of d prime is bigger or equal than f of d. So f of d prime is bigger than f of d. Now this is what we wanted to show. F of d prime should be bigger or equal than f of d. So by building this small chain of just two elements, we can show that if a function is continuous, then it's also monotonic. Okay, we have to show the other direction. So the other direction is if f is monotonic and if at least one half of this equality holds, so if we first apply LUP, least upper bound, then f, this at least is less defined or equal than if we do it the other way around, then f is also continuous. So we now assume that f is monotonic. And let this hold for all chains. For all chains S. Now we need to show that these two things are equal. And by antisymmetry, it's sufficient to show that this also holds in the other direction, so that this is less defined or equal than that. So since this relation is antisymmetric, antisymmetric means if it holds in both directions, then the two elements must be equal. Since this is antisymmetric, it suffices to show the thing in the other direction, and the other direction is first apply f and then build the least upper bound, and the result should be less defined or equal than if you do it the other way around. Okay. Now, what does this mean? This means that the least upper bound of this chain is smaller than this element over here. And if we want to show this, it's sufficient to show that this is also an upper bound of f of s. So to this end, it is enough to show that this thing on the right-hand side, so this here, is an upper bound of f of s. So of the set where we have f applied to D for all elements D of S. The reason is that if this is an upper bound of the set over here, then it must be greater or equal to the least upper bound. Since this is the smallest upper bound, so every other upper bound must be bigger. Okay, so in order to show that this is an upper bound of that, we have to show that this thing is bigger than every element of this. So we take some D out of S. and we have to show that f of d is smaller or equal than f of this upper bound. If this holds, then this is bigger than every element fd. Now, why does this hold? Oops. Why does this hold? Well, we know that f is monotonic. We somehow have to use this. And now look at these arguments. Here we have d, and there we have the least upper bound of s. D is an element of s. So d is smaller than the upper bound of any upper bound of s. So since d is smaller than the upper bound of s, monotonicity of f implies this. F of d lesser or equal than f of least upper bound. And so we have proved this direction as well. Okay, so monotonicity indeed implies this direction. And for continuity, we need the other direction as well. However, if all chains are finite, then there is no difference between monotonicity and continuity. So, in other words, when the chains are finite, we now, by A, we know what the difference between continuity and monotonicity is. Namely, it's this part on the top of this board. F of lab of S is less than lab of f of s. And this, in fact, holds whenever chains are finite. So, because of A, it's sufficient to show the following. If we have a finite chain, S, consisting of d1 to dn, where d1 is less defined or equal than d2, and this is less defined or equal than dn, and moreover, if f is monotonic, then this other missing condition holds as well, which makes the difference between monotonicity and continuity. So then we have this other condition which is on the top of this board. So it doesn't matter whether you first apply lab and then f, or do it the other way around. You have that this is less defined or equal than this. So continuity means monotonicity plus this, and if chains are finite, this additional condition is satisfied, always. Now, how do we show this? What is the reason? Well, what is f of the least upper bound? What is the least upper bound of this finite chain? Well, we had this before. The least upper bound is dn. So this is f of dn. And, well, we can see that f of dn is an element of fs. I mean, fs is the set of all, is f of d1, f of d2, until f of dn. And the least upper bound of fs is an upper bound. So every upper bound of fs must be bigger or equal than every element of fs. So therefore, if this is contained in here, then it must be smaller than every upper bound. The reason is this is an upper bound of fs. And so it must be greater than every element from fs, and this is an element of fs. And therefore, we're done. So this is true for finite chains, but not for infinite chains. The problem is that for infinite chains, if you take the least upper bound of a chain, it's not guaranteed that this least upper bound is a member of this chain. If you regard fact 0, fact 1, fact 2, fact 3, and so on, the least upper bound of this chain is fact, and that's not contained in the set fact 0, fact 1, fact 2, and so on. So by building the least upper bound, you might get a new element which is not in the chain, but that cannot happen if your chain is finite. If your chain is finite, then your least upper bound is from the chain, and then there is no difference between monotonicity and continuity. So this makes the difference. Now, how can you use this theorem in practice? Well, in practice you can, you can use it to find out whether a certain function is continuous or not. So this theorem 2.1.15 can be used in order to prove that certain functions are continuous. Here's an example. The following function, which I call ff, takes a function from z bottom to z bottom and returns a function from z bottom to z bottom. So it takes a function and returns a function. And in fact, what this ff does is, if you apply it to fact 0, then it gives you fact 1. If you apply it to fact 1, it gives you fact 2. So what it does is, if you apply it to fact n, it gives you fact n plus 1. So it transforms one approximation to the factorial function into the next approximation to the factorial function. And it is defined like this. So if you apply ff to a function g, then the outcome is another function. If you apply ff to a function, you get another function from integers to integers. So this whole thing here is a function from integers to integers. And what happens if you apply it to some integer x? So x is an integer or bottom. Well, if x is less than 0, you get 1. Otherwise, if this was the previous approximation to the factorial function, you apply the previous approximation of the factorial function to x minus 1 and multiply the whole thing by x. Otherwise, and here minus and this dot are the strict extensions of the subtraction and multiplication function. Of the subtraction and multiplication function. So if you try it out with this example and you apply ff to fact 0, then you get a new function which returns, if you apply it to a negative number, it gives you 1. If you apply it to a positive number, it calls fact 0 on x minus 1 times x. Now fact 0 is undefined, so you get fact 1. Fact 1 is defined for x less than or equal to 0 and undefined otherwise. Now if you apply ff to fact 1, you can find out that then you get fact 2. And if you apply ff to fact 2, you will get fact 3. So try it out, you can see it. And so in other words, this chain that we get here can be also obtained by applying this function ff. And then you might ask yourself the question, what about continuity here? And you can prove that ff is continuous. That ff is continuous. And if you want to prove this, directly, that is not so easy, but if you use this theorem, that is very easy. So by this theorem 2115a, so what one has to prove is that ff is monotonic. That is rather easy. And that if you first apply f, and then, if you first apply the lap and then s, then this is smaller or equal than if you do it the other way around for all chains. From z bottom to z bottom. For all chains. And this is not very difficult to do. This will this or a related exercise will be on the next exercise sheet. So you can really use this to verify that certain functions are monotonic. And we will need this function ff later on, so this will be our leading example when we define the semantics of recursively defined functions. Okay, see you on Friday.